Now I want to talk about energy and momentum in relativity. I'm not going to try and prove everything rigorously, but just show that it's plausible. So here's the metric equation. It unfortunately has a little mistake here. That should be a squared, not times 2. Alright, I'm going to take this metric equation, I'm going to divide everything by delta tau squared, and I'm going to multiply everything through by mc squared. No, m squared c squared. So I'm going to multiply everything by m squared c squared over delta tau squared. And that's going to give me this result. Now right here, I've got mc squared, and that quantity is being squared. Now the mass of an object in its own rest frame is pretty well fixed, so that's a nice constant value. But you'll notice, because it's being multiplied by a speed squared, this has the units of energy. Now when I come over here, this has the units of energy, and I've got a delta t over delta tau, and this has m times c, and then I've got a delta x over delta tau. Well, delta x over delta tau is a kind of velocity. So I've got a mass times a kind of velocity. That seems like it should be a momentum. And in fact, that is the correct momentum from a laboratory observer's point of view of a particle moving. Notice it's not delta x delta t. The velocity of the particle is delta x delta t. But if we look very carefully and watch at how much more difficult it gets to accelerate a particle as it moves faster and faster, it turns out we need to divide it not by the time in the lab frame, but the time that passes in the particle's own frame. This is generally a smaller time, which means this momentum will be bigger than if we just used v here. Delta t over delta tau, we know from earlier things we've looked at, is just 1 over, the squared is 1 over 1 minus v squared over c squared. So if we plug that in here and call this term the energy, then the energy is just mc squared times delta t over delta tau. How much time passes in the lab frame compared to how much time passes in the particle's own frame, which we can come through and put in our factor of gamma. This is mc squared over 1 minus v squared over c squared to the 1/2, or simply E equals gamma mc squared. Similarly, this delta x delta tau is just delta x over delta tau is delta x over delta t times delta t over delta tau. So that's just mv gamma, or mv over the square root of 1 minus v squared over c squared. So this is our energy, this is our momentum. Energy squared, momentum times c squared. The end result is I get this equation, that m squared c squared is e squared minus pc squared. Sometimes people that work a lot with relativity will just write this as m squared equals e squared minus p squared. They work in units where the speed of light is 1, and this is a simple relationship. First off, this tells us that the rest mass, when the momentum is 0, is just equal to mc squared. Einstein's famous equation, E equals mc squared. As we can see, this is actually just a special case of the more elaborate equation when we're dealing with something moving at high speed. Sometimes people like to say that this is the rest mass, and they like to talk about a relativistic mass that's equal to m times gamma. That actually causes a number of problems. It's not the way Einstein liked to think about it, so I'm not going to go further with that.